Welcome all. Last time we looked into the damping of the system. So, today we will incorporate the damping in our analysis and see how the results are coming out. So, let us start the class. Okay. So, today we will be doing an example covering the analysis of a multiple degree of freedom system, and today we will be including damping into the system. Okay. Last time we looked into the formulation of the frequencies and the mode shift for an undamped system, that is the damping was 0. But today we are going to include the damping of the system and see how the system is going to behave. Okay. So, we consider a set of 3 dashboards. Okay. So, these are called the dashboards. Okay. So, these are nothing but these are used to represent the viscous damping. Okay. As we discussed earlier also in the previous classes, we are talking about the viscous damping. Okay. Where the total damping force is proportional to the velocity, and this is given by an damping coefficient. Okay. So, this is the formulation of the dampers. Okay. And these dampers are represented by a viscous dampers. Okay. So, we have 3 dashboards. So, each of them are connected to the given degrees of freedom. Okay. So, one end is connected to the ground. Okay. So, this is the arrangement of the damper, and the system properties: mass is there, they are lumped at 3 positions, okay, x1, x2 and x3, x1, x2 and x3, and there is stiffness in the system. Okay. So, this represents the external or absolute damping in the system, okay, and we can represent it using there might be an internal damping also. Okay. So, this is a case of an internal damping, and this is a case of an external damping. Okay. So, damping can be represented, or damping can affect from a lot of things. Okay. So, what, as we discussed earlier also, we are trying to see the final effect of the damping. Okay. So, for the case A, okay, when we are only considering the case A, when we are only considering the external damping, okay, then the damping becomes a diagonal matrix. Okay. So, in this particular case, the damping is just acting externally at the degrees of freedom. Okay. There is no coupling between the respective dampings. Okay. So, in this case, there will be only diagonal terms corresponding to the each degree of freedom system. Okay. So, the damping matrix takes the same structure as the mass matrix. Okay. Additionally, if every element in the system shares an identical ratio of damping to the mass, the damping matrix C will be directly proportional to the mass matrix. Okay. So, it means that if there is a ratio, okay, if there exists a ratio x between the damping and the mass, okay, so then the damping matrix, okay, C can be represented as an factor of the mass matrix. Okay. So, this thing is called the mass proportional matrix. Okay. It means that I am assuming my damping coefficient is proportional to the mass. Okay. So, this is the mass proportional matrix. Okay. So, if I look into the case B, okay, so then the damping coefficient or the damping matrix is a coupled matrix. Okay. It means that here, if we take this thing out, okay, take this thing out, and if the forces are applied here, the acceleration is applied in this sense, then the damping will be from the 2 ends. Okay. So, there will be a damping force here also, and there will be a damping force here also, okay, due to the relative motion of the system. Okay. So, then the system becomes coupled like a stiffness matrix. Okay. So, here the damping will show a nature similar to the stiffness matrix. Okay. So, it can be a function of the stiffness matrix. Okay. So, now here the damping matrix can be constructed in a similar manner to the stiffness matrix. Okay. So, it will have a similar formulation. Okay. So, here if stiffness matrix is K1, K2, X1, X2, X3, okay, minus K2, 0, minus K2, and so on and so forth. So, the structure of the damping matrix and the stiffness matrix will follow a similar pattern. Okay. And if every dashpot and spring in the system, it means that if every C and K in the system maintains the same ratio, then the damping matrix become proportional to the stiffness matrix. C will be a function of the stiffness matrix. Okay. In the previous case, C was proportional to the mass matrix if it is was applied in an external sense, and in this particular case C is proportional to the stiffness matrix if it is applied in an internal sense. Okay. So, we have two things now. The damping matrix can be a mass proportional matrix or it can be a stiffness proportional matrix. Okay. So, generally the damping matrix C may differ in structure from both the mass matrix and the stiffness matrix. Okay. An example configuration of the dashboard that results in such a damping matrix is illustrated in figure C. Okay. So, in this particular case the damping matrix is proportional to the mass matrix. In this particular case the damping matrix is proportional to the stiffness matrix, and in this particular case, okay, the damping matrix is neither proportional to the mass matrix, neither it is proportional to the stiffness matrix. Okay. So, the damping may take any formulation, okay, depending upon how the system is going to behave. Okay. It can be proportional to mass, it can be proportional to stiffness, or it can be neither proportional to the mass or the stiffness. Okay. When damping in a structure arises solely from the resistance of the surrounding fluid, it is appropriate to assume that C has the same form as the mass matrix. Okay. So, this is a particular case in which C is proportional to the mass matrix, okay, and it will happen when the damping is only due to the resistance of the surrounding fluid. Okay. If there is only resistance due to the externally applied any fluid, if it exists, okay, or if it is kept in a scenario, okay, where only the damping is due to only the external components, okay, at each degree of freedom, then the damping will be proportional to the mass. Okay. Conversely, if the damping is entirely due to the energy dissipation through deformation of the structural member, okay, the damping is due to the relative motion of the structure, okay, is entirely due to the energy dissipation through deformation of the structural members, meaning that the damping is due to the only due to the whatever energy loss is occurring, it is occurring due to the deformation in the structure. Okay. Then the damping matrix can be considered to mirror the stiffness matrix, okay, as in the case B. Okay. So, in the case B, if we see, the damping is proportional to the stiffness. Okay. So, all the damping component, okay, all the dissipation of the energy will occur due to the relative motion in the system. Okay. So, due to the relative motion in the system, there will be a stiffness matrix, and due to the relative motion, okay, due to the velocity, there will be an energy dissipation in the form of the damping. Okay. So, here in this particular case, the damping matrix becomes proportional to the stiffness matrix. Okay. So, cases where the damping matrix is either mass proportional or stiffness proportional matrix are specific instances within this border classification. Okay. So, if due to the external fluid resistance, the damping matrix becomes proportional to the mass matrix, due to the internal energy dissipation due to the relative motion, the damping matrix becomes proportional to the stiffness matrix. Okay. So, these are the two extreme cases, okay, where the damping matrix becomes proportional to the mass or the stiffness matrix. Generally, they are somewhere in between. Okay. The damping matrix normally is represented as a combination of the proportionality to the mass matrix and the stiffness matrix both. Okay. So, in reality, the damping matrix will be a combination of the both mass and the stiffness matrices. Okay. The modal supervision method used for the undamped system can also be applied to the damped system if the damping matrix C satisfy the orthogonality condition. Okay. So, the same theory we are going to apply for the damping also. Okay. So, in the mass matrix, in the stiffness matrix, we saw that if we multiply it with the different modes, okay, phi r, phi r, phi s, phi s. Okay. If this is happening, then due to orthogonality, this terms will be 0. Okay. So, the same thing can be applied for the damping matrix also. So, here we can use this expression to denote the contribution of the ratio of the mass and the damping. Okay. So, this is the ratio of the mass and damping, and we can substitute this back in this particular equation and calculate the equation of motion for the particular mode, okay, where zeta represents the percentage of the critical coefficient of damping for motion in the RF natural mode, and tau r is the participation factor. So, participation factor we already saw, and zeta is nothing but the damping coefficient divided by the critical damping. Okay. So, this is the zeta. Okay. So, this we have already seen in case of the single degree of freedom approximation. Okay. So, same thing we are applying and we are using for the multiple degree of freedom system. So, moving ahead. So, if C, the damping is proportional to either mass or stiffness, or as we discussed earlier, or is a linear combination of mass and stiffness. So, it can be expressed in this term. Okay. So, either the damping can be proportional to the mass, or damping can be proportional to the stiffness, or in most of the practical cases damping is a linear combination of the mass and stiffness both. Okay. So, in this case what we need to do is that we know the mass matrix, we know the stiffness matrix, we need to evaluate the alpha and beta, the coefficients, and we can express C as a combination of the mass and stiffness matrix. Okay. So, alpha and beta are constants, and it is clear that the damping matrix is going to satisfy the orthogonality relation defined by equation 45. Okay. So, substituting equation 48 into 45, okay, we obtain this particular case. Okay. The result is 0 because each of the triple product equals to 0. Okay. So, this one is 0 due to orthogonality, this one is 0 due to orthogonality. So, in turn everything will be equal to 0, and C is going to satisfy the orthogonality also. So, C will satisfy the orthogonality criteria as well. So, this is called a Rayleigh damping. Okay. So, in the Rayleigh damping, the damping is proportional to mass and stiffness both. Okay. So, damping is a linear combination of the mass and stiffness, and it is called a Rayleigh damping, and it satisfies the orthogonality condition. So, damping ratio zeta for a mode with natural frequency omega is then, okay. So, zeta, that is C divided by C critical. Okay. So, then this becomes, this is given by this particular equation, okay, or zeta equals to this particular equation. Okay. So, here if we look into this particular term, okay, if damping is mass proportional, then beta equals to 0. Okay. So, only this term will remain, and this will give a mass proportional damping. Okay. If the damping matrix is a stiffness proportional damping, okay, it means then alpha will be equal to 0, and only this term is going to remain. Okay. So, in this case the damping factor is proportional to the natural frequency. So, zeta p will be proportional to omega p, and in the case of a mass proportional damping, zeta will be inversely proportional to the frequency. Okay. So, depending upon what is happening, okay, either the damping factor will be directly proportional or inversely proportional to the frequency. Okay. And if both are there, okay, so then it will be a linear combination of the both. Okay. So, this is called the Rayleigh damping. Okay. So, this is the representation of the zeta, okay, the damping coefficient or the damping factor with respect to the omega, that is the frequency. Okay. So, for C equals to alpha n, okay, it will be in this phase. Okay. So, this line gives C equals to beta k. Okay. So, for a given excitation, it can be observed that the higher modes will be damped significantly more in the second case than in the first case. Okay. So, this is how the Rayleigh damping has been represented out here. So, here what we will try to do is that we will try to evaluate the Rayleigh damping. Okay. So, in a 2 degree of freedom system with arbitrary modal damping factor zeta 1 and zeta 2. Okay. Let us say that we have a 2 degree of freedom system and it has arbitrary damping factors zeta 1 and zeta 2. Okay. So, here in this case it is always possible to determine a Rayleigh type damping matrix, okay. And what it should do is that it should satisfy these two equations, okay, for P1 and P2, okay. So, for the two frequencies we write down the value of zeta 1 and zeta 2, okay. And then using these two equations we solve them simultaneously, and here we can calculate the value of alpha and beta as a function of omega and zeta, okay. So, if we have the factors zeta 1 and zeta 2, okay, we can represent the whole system as a linear combination of the mass and stiffness matrix, okay, and we can evaluate the coefficients, the linear coefficients alpha and beta, okay, and these are the solutions for the alpha and beta, okay. In the special case, okay, where zeta 2 and zeta 1 have this relationship, okay, beta equals to 0 indicates that C is proportional to the mass matrix, okay, and this is the value of the coefficient alpha, okay. Similarly, if alpha equals to 0, the C matrix will be proportional to the stiffness matrix, and this will be the value of beta, okay. So, for systems with more than 2 degrees of freedom, okay, where the modal damping factors are arbitrary, it is generally impossible to obtain the Rayleigh type damping matrix, okay. So, the Rayleigh type damping matrix works very well when we have 2 degrees of freedom, okay, but when the degrees of freedom becomes more, okay, it becomes more and more difficult to obtain a Rayleigh type of damping matrix, okay. So, now we looked into the formulation of the mass matrix, we looked into the formulation of the stiffness matrix, we have looked into the formulation of the damping matrix, we evaluated the frequency of the system, we evaluated the mode shifts of the system, okay, and we tried to write down the damping matrix as a function of the mass matrix, we try to write down the damping matrix as a function of stiffness matrix, or in the case of a Rayleigh type of damping where the damping can be written as a function of the mass and stiffness both, okay. So, after that all these things now we will use in order to evaluate the response of the structural elements subject to impact, okay. So, impact load already we have been dealing with, okay. So, we will review what is an impact load, okay. So, an impact load is a force applied suddenly over a very short time, okay. So, impact load can be represented by this type of notation, okay, where the impact has been applied suddenly over a time t, okay. So, this time t duration is very less and the magnitude of F is very high, okay. So, force applied suddenly over a very short time. So, this t is very short, okay. So, impact is normally coming from the collision type of event or sudden contact between the two bodies, okay. So, unlike static or gradual loading, impact load causes the dynamic effect, okay. Impact load is going to cause the vibration and the propagation of the stress waves in the system, as we have seen earlier also, okay. So, this effects leads to the rapid deformation and possible damage in the structure, okay. So, due to the rapid deformation we can see that the application, the magnitude of the force is very high and it is applied in a very short time. So, if we try to evaluate the response of the system with respect to the static case, then the value of x it will be significantly higher than the static value, okay. So, this deformation can be very large, it will also evolve very rapidly, meaning that it will evolve in a very short period of time, okay, and it will cause damage to the structure, okay. It means that the stresses or the deflection limits will be exceeded in case of the impact. If the value of the force is large, okay, then the value of the permissible stresses or the value of the permissible deformation will be easily reached and it might cause the damage in the structure. So, impact transfers kinetic energy producing significant stresses, okay. So, due to the rapid event, okay. So, let us say a mass m is moving with a velocity v, okay. So, here the kinetic energy transfer will be half mv square, okay, and if the velocity is large, okay, so then there will be a high amount of kinetic energy transfer to the existing static system, okay. and it will produce the significant stresses in the system, which might lead to the damage in the system. Okay. The factor influencing impact effects include force magnitude. Okay. So, if the force is high, the value of the impact will be high, duration, okay, and the time duration or the application of the load, velocity, the velocity by which the system is moving, mass of the system, mass of the impactor system, and the contact area, the area over which the contact occurs. Okay. So, if the contact area is very less, then this high amount of energy will be transferred to this very small area, which might lead to a sudden and drastic failure. Okay. So, now we compare the static versus impact loading. Okay. So, the load application. Okay. In a static sense, the load is applied over a gradual sense. Okay. In the impact loading, the load is applied sudden and with a high speed. Okay. So, if we try to compare the load application of a static load, okay, or a so called static load, we will see that the load is applied over a large amount of time t. Okay. So, if this is the magnitude of f, okay, it is applied over a significant amount of time t. Okay. But in case of an impact load, f will be applied very rapidly. Okay. This will be the f and this will be time t. So, this time t might be in milliseconds, okay, and this time t might be in hours. Okay. So, the application of the load, here it is gradual, here it is applied in a sudden sense. Okay. The magnitude of the force, okay, this is predictable and with a lower quantity. Okay. In case of the impact load, due to the kinetic energy, the magnitude of this force, okay, this is static force, this is dynamic force or the impact force. So, Fi will be significantly higher than the static force. Okay. So, the magnitude itself is very high in case of the impact load. Okay. It is applied over a very short duration of time, okay, whereas in case of the static force, the force is applied over a gradual time and its magnitude is very less. Structural response. Okay. So, structural response in what is known as the quasi-static deformation, and in this particular case of the impact loading, the structure is going to vibrate, okay, and the stress is going to occur. So, here what is going to happen is that the structure will start to vibrate, okay, but since the loading is applied gradually and it has a low magnitude, the transients will die down. Okay. So, only the steady state with a less magnitude. Okay. Let us say this is the deformation. So, then this will be proportional to f over k. So, this will remain in case of the static sense, but in case of the dynamic sense, there will be high amplification in the system and this is going to vibrate violently. Okay. And as such, there will be high stresses also evolved in the system. Okay. The stress waves are going to transfer in the system. So, the value of the x dynamic will be very high. Okay. It will occur in a very short period of time and it will cause the stress waves also to generate in the system. Okay. How we deal with the system? The analysis method, we can normally do a static analysis where we can use the equation force is proportional to the stiffness. Okay. Force is directly proportional to the deformation in the system and constant of proportionality is the stiffness in the system. Okay. So, we can use this equation, okay, but in case of impact we will have to use the dynamic equation of motion. Okay, P of t. Okay. So, we will have to use the dynamic equation of motion. Okay. So, this becomes a dynamic analysis where this remains as a static only analysis. Okay. So, this is the short comparison between the static and the impact loading. So, energy exchanges and losses. Okay. So, energy distribution, the forces during impact only exchange momentum energy between the system components. Okay. So, in case of the elastic impacts, most of the energy is recovered. In plastic impacts, significant energy is dissipated. Okay. In the plastic deformation during impact results in energy loss as the dissipative forces. Okay. So, if a mass m is going to hit m1 is going to hit m2. Okay. So, this is the approach period, okay, and after that this is the restitution period. Okay. So, this is the maximum approach period, okay. And here in case of perfectly elastic impact, okay, all the deformation is recovered, okay. But in case of the plastic deformation, okay, there is a permanent deformation in the system, okay. So, elastic impact, and if this is a perfectly plastic impact, okay. So, if whole of the system goes into the plastic region, okay, there is no recovery in the system, okay, and there will be a permanent deformation in the system, okay. So, whatever is the thing achieved at the approach, this becomes the permanent deformation in the system, whereas in the elastic impact, okay, the deformation comes back to its original state, okay. If we started from here, then it will go maximum, and then there will be a restitution period and everything will be recovered, okay. For a case of perfectly elastoplastic analysis, okay, there will be some permanent deformation and some recovery will be there, okay. So, this is the deformation history, okay, deformation over time, okay. So, this is the approach period, this is the restitution period, okay. Okay. So, we look into the Carnot's law and the impulse work theorem, okay. So, Carnot's law deals with the kinetic energy loss, okay. So, the difference in the kinetic energy before and after impact relates to the energy lost due to the plastic deformation, okay. So, the difference in the kinetic energy before impact and difference in the with respect to the kinetic. So, if this is the kinetic energy initial and if this is the kinetic energy final, okay, this difference relates to the energy lost, okay. So, if there is a difference between the initial and the final energy, it means that the energy has been lost in the system, okay. So, if we are trying to see the equation, okay. So, this is the equation given by the system, okay. So, this difference in the kinetic energy, okay, before and after impact relates to the total loss in the system. Okay. So, if impulse act under conditions where no work is done, okay, their contribution to the energy balance vanishes, okay. So, the corresponding equation relating angular impulse and energy before and after impact is given by these two terms, okay. So, Hertz law of impact, we have already seen the Hertz law of impact. So, the key assumptions in the Hertz law of impact is that the bodies are smooth and elastic with curved surface, okay. So, they are often assumed as spherical or cylindrical, okay. No friction is considered between the contacting surfaces, okay. So, the friction between the surfaces is ignored, okay. Only the normal forces are being considered, okay. The contact area is small compared to the object size, okay. So, the contact area between the impacting bodies is assumed to be small, okay. It means that we are looking into the localized deformation, okay. The strains and the stresses near the contact area are assumed similar to those under static pressure, okay. So, if we are taking two spheres or a sphere and a flat surface, okay, maybe two spheres or a sphere and a flat surface, the contact force is given by this equation, okay, where F is the normal contact force, delta is the deformation or approach distance, okay. So, and the K is the contact stiffness coefficient, okay. So, it depends upon the geometry of both the materials, okay, and the material properties, okay, of both the surfaces, okay. So, basically what we are saying is that the contact force is proportional to the deformation raised to the 1.5 or 3/2 power, okay. So, this is basically a power law which is known as the Hertz law of impact, okay. And in order to evaluate K, we know the geometry of the bodies, okay. Let us say sphere to sphere contact, sphere to flat contact, and so on and so forth. So, K becomes a function of the geometry and it also becomes a function of the inherent material properties, okay. This might be aluminum, this might be steel, this might be steel, this might be steel, okay. So, depending upon whatever material is being used, okay, we can calculate the contact stiffness, okay. So, the coefficient of the contact stiffness can be calculated depending upon the geometry and depending upon the material, and this represents the Hertz law. Okay. So, if you look into the Hertz law for the purely elastic impact, Hertz law will be giving a proper bell curve, okay. And for depending upon how the elastic behavior is affected, okay, the other iterations, these things can be used to evaluate the contact force relationship. Okay. So, Hertz law primarily gives the evolution of the contact force, okay, when two bodies are in contact. Okay. So, this is a powerful law to calculate the contact forces, okay. And this contact forces, we can use this thing to give the magnitude of the externally applied load, okay, in a system, because whenever we are dealing with an impact type of situation, what we have is an externally applied mass coming with a velocity, okay. But if we have to calculate the contact forces, we can use the Hertz law and calculate the contact forces, and that thing we can put it as a forcing function in the analysis of a multiple degree of freedom system analysis. Okay. So, for that we need to know the contact stiffness, which in turn will depend upon the geometry of the system, okay. That is, let us say two spheres, aluminum and steel, are acting on each another, and the material properties, okay, the grade of the steel, the Young's modulus of the steel, and the Poisson's ratio of the steel, or any other two materials which are in contact. Okay. So, today we looked into different types of damping, and then we looked into the different impact laws. We looked into the Hertz contact law. From the Hertz contact law, we can evaluate the contact forces. So, go through the lectures, and we will stop here and we will continue from the next time. Thank you.